Welcome to a video lecture of EE351. In this video, I will discuss an example of DC to AC converters. So this is the question is given here. A single phase half bridge voltage source inverter is connected to a 48 volt DC supply, and the load is 2.4 ohm, that is a resistive load, and square wave switching is used as the switching mechanism. So you are asked to calculate the RMS of the output voltage, RMS of the fundamental component of the output voltage, output power, average and peak currents of each power electronic switch, then peak reverse blocking voltage of each power electronic switch, and finally you are asked to calculate what is the uh, total harmonic distortion. Okay, so we will discuss the question. First I will draw the schematic diagram of half bridge DC to AC converter. So you have two capacitors which are split up, and then you have the power electronic switches. You have two power electronic switches, Q1 and Q2. So you get the midpoint at the as the output, and you connect a resistive load. You get the midpoint of the capacitors, and so this is the output. So this is the output current and the output voltage. So you have the load resistance R, then you have the DC voltage VDC to capacitors. Okay, so first now the information given are VDC is equals to 48 volts, and this load resistor is equals to 2.5 ohms. So those are the information that are given for you, and the other information is the square wave switching. So if we recall our theory, for the first one, when we do the square wave switching, what you would get at the output is now if we draw the waveforms, if we take Q1 as 1 0 in this form, 1 0, then when we switch the waveform, we have V out, which is going to be in this manner. So you have VDC by 2 minus VDC by 2 because of the capacitors. It is being the voltage is splitted. So the output voltage RMS we can express as VDC by 2. So this would be equals to 48 divided by 2, which is equals to 24 volts. So I think that is straightforward. Then if we consider the second one is the RMS of the fundamental component. So if we recall the theory, we get the output voltage can be expressed as sinusoidal components, addition of sinusoidal component 135 to infinity 2 VDC over N phi sin N omega N omega t. So that's how we can express. So we could express the peak of the nth harmonic as 2 VDC over N phi. So we could write the RMS of the nth harmonic as square root 2 VDC over N phi, because if we divide by root 2 we will get the RMS value. So here you are asked to calculate the fundamental component RS. So then this N is going to be equals to 1. So you have root 2 VDC over 5. So you can do the calculation of this one. Root 2 into 48 divided by 5. So here what you would get is root 2. If we substitute, you would get 48 divided by 5. So this is going to be equals to 21.6 volts. So that's the fundamental component, RMS voltage. So we calculated the first one. Now we calculated the second one. Then you are asked to calculate what would be the output power. So we could write P output as P squared over R. So the output voltage is squared over R. So the output voltage is 24, which we calculated here, and the resistance is 2.4. So we can calculate this one. 24 squared divided by 2.4 is going to be 240 watt. So that's the output power from this inverter. So we calculated this one. Then you are asked to calculate the average and peak currents of each power electronic switch. So you have, this is the output voltage waveform. So from this one actually you can get the output current waveform as well. What the only difference would be now is that the magnitude would be different, but you would have the same shape. So it is going to have a similar shape here. So this would be your output current waveform. So if I mark this value as I is that is the peak of one instant. So we could write I as V over VDC. Now this, the voltage at this time is VDC by 2. So we have VDC by 2 divided by the resistance of the load resistance. So I use the variables itself. You have the R. So now we this is going to be 24 VDC. Then we have 22.4 is the resistance. So here VDC is 48. So VDC by 2 is 24 divided by 2.4. So the peak current flowing through a switch is going to be equals to 10 amperes. So when switch Q1 is turned on, current will flow through the switch Q1 and it is 10 amperes. And when switch Q2 is turned on, the current is output current is minus I value. So that would be again equals to VDC by 2 over R. So that's the peak current. Then you need to calculate what would be the average current flowing through a switch. So I switch average. So this is the current flowing through output current. So if we plot the current flowing through a single switch, it is going to be in this way. So this is the I switch Q1. Okay, so similar shape will be there for the current flowing through the switch Q2. Now we can calculate what would be the I switch average. So it is only conducting for a half of the period. So the average would be equals to 10 divided by 2, which is equals to 5 amperes. Whereas what you could in what you could write is here is I times Ps by 2 divided by Ps. So that's what happens. So that would be equals to I by 2, I peak by 2, that is equals to 5 amperes. Okay, so that's the answer for the question number D. Okay, so we calculated the average and the peak currents flowing through the switch. Now the next one is asking peak reverse blocking voltage of each power electronic switch. So when a switch is turned off, what would be the voltage appearing across the switch? So that's the part number E. So what we need to do is we need to consider two cases. In the first case, this is the switch Q1 and this is switch Q2. So we are going to close this switch. So when we close this switch, now this is VDC and this is 0. So when we switch, the switch is turned on, the voltage at this point would be equals to VDC. So the voltage across the switch is going to be VDC. Then when we consider the other instant where we turn on the lower switch, in the other instant we are going to turn on the next switch. What we are going to do is we are going to close this switch. So this is 0 and this is VDC. Now when we turn on this switch, the voltage at this point would be 0 volts. So now again what the voltage that would be appearing across this switch is going to be equals to VDC. So if we turn on switch Q1, VDC voltage would appear across switch Q2. If we turn on the switch Q2, the voltage appearing across the switch Q1 will be equals to VDC. Therefore, the blocking voltage that power electronic switch will experience would be equals to 48 volts or VDC voltage. So that's the answer for uh, the part E, where the peak reverse blocking voltage of each power electronic switch. Now finally you are asked to calculate what is the total harmonic distortion. So which is abbreviated as THD. Now this THD can be defined for voltage and current both, but here I'm in this one I'm trying to calculate what would be the total harmonic distortion of the voltage. So the definition of total harmonic distortion is sigma n equals 2, 3, etc. to infinity VON. So that means what we do is we consider the harmonics 2, 3, 4, etc. to infinity. So you get the RMS of each harmonic component and we square it. Then we add them together, and after that we get the square root of that, and this value will be divided by the RMS of the fundamental component. So this is the definition of the uh, THD value. So when you want to calculate the THD value, we need to calculate, we have already calculated VO1, but we haven't calculated this harmonic addition, so we need to calculate that first. So when we consider a waveform, we can write the total RMS squared as addition of the squares of the harmonic component. So VO1, VO2 is squared, VO3 is squared, etc. So what we could write here is as VO1 squared sigma I going from I2 3 infinity VO n squared. So now this is the component that we need. So sigma n I going from 2 3 to infinity, VON squared is going to be equals to V out squared minus VO1 squared. Okay, so we need to calculate the square root of that. Sigma I going from 2, 3 to infinity, VON squared is equals to square root V out squared minus V out fundamental squared and square root of that. So V out is RMS is 24. So 24 squared minus VO1 we calculated earlier as 21.6. So here we have 21.6 squared. So if we calculate this one, we will get 24 squared minus 21.6 squared, and the square root of that is going to be equals to 10.5. Now to calculate the THD, what we need to do is we need to divide this value by the fundamental component, which is 21.6. So that would be equals to 10.5 divided by 21.6 is 0.486. So usually we represent the THD as a percentage value. Then we have to get 0.486 into 100, which is equals to 48.6. Okay, so now in this example, we consider the half bridge uh, voltage source inverter, and we use the square wave switch in, and with the resistive load we calculated the fundamental component voltage, current, then the power, output power, then the currents flow into the switch, voltage across the switch, then finally we calculated the total harmonic distortion. So with that I will conclude this video. Thank you.